So here, the target architecture must be well understood, because now remember, we've now moved from language independent representation, which is intermediate code, to now machine dependent representation. So we must understand the target architecture very well. And the things here we must address. So first, in fact, in terms of the target architecture, the code generator is expected to have an understanding of the target machine's runtime environment. It also should have an understanding of the instruction set, because of course different architectures have different instruction sets. So now we are very specific to a particular architecture. Yeah. So being aware of the nature of the target language for which the code is to be transformed can help us in determining machine-specific instructions, so that we're able to generate code that utilizes the target architecture more conveniently. So note that the target machine can either be a CISC or a RISC processor architecture, and that has implications as to how we generate the code. Okay. So the things that we must focus on, or code generation has to address, are largely three. First, there's selecting the instruction. So we're going to map the intermediate code instruction into a target architecture instruction set. Then there must be the notion of register allocation, and also how we schedule the instructions. Okay, so for instruction selection, we know that one intermediate code instruction can have many instructions that it can map to onto the target architecture. So it becomes the responsibility of the code generator to choose which instructions from the target architecture it's going to map the intermediate code instructions to. Then for register allocation, we know that a program has a number of values that must be maintained during the execution based on how the code has been written. So the target machine's architecture may not allow all of these values to be kept in the CPU memory or in the registers. So the code generator must decide which values should be kept in the registers, and also the registers that are going to be used for these values. So some values will be stored in other memory locations. They could be in memory, it could be in a heap, it could be in a stack, it could be in a register. And that is actually the work of the compiler. The code generator must make those decisions first, which values must be maintained for execution, where those values will be stored. Will they be in registers? Will they be in memory? Where will they be? And keeping track of where those locations are. And then under instruction scheduling, the code generator must decide the order in which the instructions will be executed. And we'll see that this is very important when you consider the types of architecture. We've already done computer architecture, so we understand about instruction pipelining and all that, depending on the capability of the target architecture. So what is now should be very clear is that when we talk about now code generation, we are no longer being machine independent. We are now very machine dependent, because we're coming up now with instructions to run on a specific architecture. So we must be very familiar with the target architecture in terms of the registers it has, the instruction set it has, and how to schedule instructions to take advantage of the architecture. If it's a CISC or it's a RISC, or you can do pipelining, etc. Okay. So let's talk about the first bit, which is instruction selection. Okay. Now, for instruction selection, we know that there could be, as I've said earlier, for one intermediate code instruction, there could be many potential candidates from the target architecture. Yeah, one intermediate code instruction can have many ways of converting it to on the target architecture. So it's the work of the code generator to choose the appropriate instructions wisely. Yeah. Why are we talking about wise selection? Because we know that different instructions have different costs in terms of memory as well as execution time. They have certain constraints, so you have to choose one that minimizes the cost and enhances efficiency. The cost could also be influenced by the surrounding context in terms of maybe what variables are needed, where are they, do you need a memory fetch, etc. So different architectures have different needs that must be considered. And here we're talking about speed, power constraints, space, etc. So as we're making the choice, as we write our code generator, we have to bear all these in mind. So it's one of the most complicated parts of the compiler is the code generator, because now it has to be very specific for a given architecture. So that's under instruction selection. So the next thing we have to talk about is the instruction scheduling. Okay. So under instruction scheduling, here basically we are asking what is the order, what is the best order of scheduling our instructions so that they utilize the target architecture resources in the most efficient way. Okay. So the code generator must decide the order in which the instructions will be executed, and it creates the schedule for instructions so that we see in what order the instructions will be executed. So here the architecture, of course, is very, very key because you want to take advantage of specific architecture. So for instance, if you have the reduced instruction set architecture, the RISC, we know that it allows for pipelining. So RISC processors only use simple instructions that can be executed within one clock cycle. And since these instructions execute in a uniform amount of time, that is one clock pulse, we know we're able to do pipelining in contrast with the CISC architecture, where the emphasis is on building complex instructions directly into the hardware. So if you're generating code for a RISC architecture, then you have to, it's good to take advantage of the ability to do pipelining of instructions as opposed to if you're generating code for a CISC architecture. Then the other architecture is the vector processing. So if you remember from your previous courses, a vector processor, also known as an array processor, it implements an instruction set that operates on 1D array of data, which we call vectors. So of course, if that is the architecture you're targeting, then you have to be aware of what are the features and what can you take advantage of, what is unique to vector processors. Then lastly, we talk about superscalar and very long instruction word architectures. So these are parallel architecture models, and they're both capable of executing multiple instructions in one cycle. So in that sense, then you have to be able to schedule multiple instructions that can be done in one cycle. Yeah. So here we're basically saying we're no longer now just machine independent. We are now very machine dependent, and the compiler or the code generator must be very knowledgeable or aware of the architecture that it's targeting the code for, and then take advantage of the features or the resources and the constraints that come with that architecture. So the last aspect when we're talking about code generation that we have to handle is register allocation. And this is actually a very complicated and very important because you know that the processors have bounded number of registers. So how do we use them? How do we allocate? When do we decide what value is going to be stored in what register? So here, the issues around register allocation. We know that a program has a number of values that must be maintained during execution. So the target machine's architecture may not allow all of the values to be kept in the CPU, memory, or in the registers. So the code generator has to decide which values to keep in the registers. And also it has to decide the registers to be used to keep these values, and also have a way of keeping track of which value is stored in which register. Yeah. So here the complications are that there are some special purpose registers depending on the architecture. So we have to make sure that we are using them for the right purpose as intended. And then also we know that there are operators that can require multiple registers. So even as you're doing the allocation, you have to look at the operation that's being done. And if it requires multiple registers, and be able to allocate multiple registers as necessary. So how do we undertake? So we've understood the three main things. There's instruction selection, there's instruction scheduling, and register allocation. So how do we then generate code? Yeah. Um, how do we generate the code? Remember, we're now moving from intermediate code to the target code. So what is the approach? So one way is what is called the naive approach to code generation. And this is all just exactly what we did for generating the three address code from the abstract syntax tree. So this simple algorithm basically says for each intermediate code statement type, generate a sequence of target code instructions. So you're guided, you just go intermediate code instruction by instruction. And depending on the type of the instruction, there's a set sequence of target code instructions that we must generate. And so that's the same approach that we used when we were generating the intermediate code. That means for each AST node, we had a sequence of three address code instructions to come to generate. So the question is, why is this not sufficient? Why are we saying it is naive? What do we foresee as being the challenge of this approach? Anyone? So of course, if we do it this way, and that was the same problem we highlighted from AST to 3-address code, is that it is so localized because it's only considering the current statement to generate the sequence. So we don't have a global view of the entire code. So we are not able to account for the global requirements of the code as well as the future requirements of data. Yeah, you don't know whether you might store something which is going to be actually used in the next instruction. Yeah, so that's why we are saying it's naive and it's expensive, and that we now need a better way to do this. So, for example, the examples we're using for SPIM, I think we've already seen this, that the SPIM assembly language, this is a target. We know that it's byte addressable with 4-byte words. There are some general purpose registers, and then we have the 3-address instructions. So we have the quadruples. So the operator, the destination, and the 2 sources for the 2 operands. So if we're to use the naive approach, this is how it would proceed. So for instance, if what we're saying is that we're going to define a target code sequence for each intermediate code statement type. So if, for example, our intermediate statement type is an assignment statement, so A is assigned the value of B, then we'll just generate 2 instructions that are target for our target code. First, we'd have a load word, so we'd load the value of B into T naught, and then we would do a store word from T naught into A. If you have A is assigned BC, so this is an array access. So of course, we'd have to compute the address first. So you load the address of B into T naught, then you load C into T1, then you add so that you figure out what you're able now to get the address. So add T1 to T naught and store the value in T naught. Then now we reference the memory, the value in the register, use that as a memory address, and load the word referenced by that memory value and store that into T naught, and then save that into A, the memory location that's been allocated for A. Yeah, so you can see what we're saying when we say it's naive. It's for each statement, there's a specific sequence of target code instructions that we have to generate. So it's easy because if it's an array, you just know you have to come up with 5 statements. If it's just an assign, 2 statements. If it's addition, you have 4 statements like that's shown over here. So if it's for addition, we're basically saying you have to load one operand into a register, so B into T naught, C into register T1. Then you do the addition T1 and T naught, store the result in T naught, and then you store the word into memory location for variable A. Yeah, so and then the same thing, this is an assignment into an array. So basically we're saying for each type of intermediate code statement, there is a sequence of correlated target code instructions. And that is that it is naive because you can see it generates very many, it's generating very many instructions. So here you can see if this is a statement, for example, if this is a intermediate code statement, so you can see we're doing step by step. So the first thing, we're going to create a temporary one, which is going to have the value of CK, and it's going to give us those 5 statements. And then we assign T2 to the value of D, T1, gives us another 5 statements. And then finally, assign AI to T2, another 5 statements. Yeah. So if we do this, you can see we've used 15 instructions. We have 12 load and store instructions and 3 arithmetic instructions. We've also allocated space for 2 temporaries, that's T1 and T2. And we've used 2 registers. Yeah. So from one intermediate code statement, you can see we have 15 target code instructions or statements that we have to generate. So that's why we're saying it's naive, because it's quite duplicated. So the problems with this approach: local decisions do not produce good code, because if you look at this, we don't have to store the word and then load it again. Yeah, here we're having to store, because that's the naive approach for this kind of a statement, as we saw here. For this kind of a statement, we have to generate the 5. Yeah, we're not sure, we are not even checking. Maybe this A is going to be used in the next, so you don't need to write it to memory. You can leave it on the register. That's what we're saying. Local decisions do not produce good code. So it does not take temporary variables into account. So we need to find a way to take them into account and get rid of the many reduced loads and stores. So this would be an improved version, where instead of storing the word, we just know we need to hold that result. So here we know that T naught holds the result of this instruction. So we leave it there, and then you just reuse it in the next place where you're adding. Yeah. So once you do this, if you take advantage of the future uses of the data and you have a global view of what's happening, you're able to generate much more compact code. So in fact, this is like almost half the instructions. Yeah, we've gotten rid of many load words and loads and store words especially. And we know also that writing and reading from memory is expensive in terms of time. So if we reduce that, then we have more efficient code. So basically, as I was saying, the naive approach is not always the best. It's simple, very easy to implement, but it will result in very bulky code that's not very efficient. And remember, for the compiler, we are very alive to the fact that we need to generate code that is just give me a second. Code that is actually fast in execution. Yeah. So we want to always have code that results in fast execution times, which is what we want to do. So we need a way to generate machine code based on the past and future uses of the data. So we want to look beyond the current instruction. So how do we do this? We need to have a way to analyze the intermediate code, to have a global view of what is happening. And then we use the results of those analyses to guide the issues, the register allocation, the instruction scheduling, and the instruction selection, because we are aware what is coming next. Okay. So how do we do that? So one way to do analysis of the code is to come up with what is called a control flow graph. Okay. So a control flow graph, it's interesting, it's the same acronym for CFG, what we've been calling a context-free grammar. So in this case, in this context, is actually a control flow graph. So it's a 3-tuple machine. We define vertices, we define edges, and we define entries. So V are nodes representing a block of related statements or instructions. So we call it a basic block, and in the next slide we'll show how we determine a basic block. So we have our vertices on nodes because it's a graph. So each of these nodes is representing a group of statements. And then we have edges, which is a that shows the flow of control between the different nodes. So maybe once you're done with the statements that are here, you can come to the next group of statements that are represented by vertex 2. From vertex 2, you could go to 3 or you could go to 4. So that's a conditional. Of course, you can see this is a conditional jump. Either come here or you come here. Or from here, you go back here and stuff like that. So once we're able to create these basic blocks, we're then able to show the flow of control. And now with this information, we know that a result that is calculated here would maybe be used here. So then that guides us on what we are going to do, what we need to leave in registers, what we need to write to memory. If we see that there's something that's not needed in stage 2, we can discard it and free up. We know that we can reuse the memory where those values that were here are needed. So that's really the utility of doing the CFG. It allows us to figure out what's coming next And therefore, what do we do with the values we are computing here? The same thing here. From 2, we know that we could either go to 4, we could either go to 3. So that decision will help us figure out what to do with the values that we compute here, and so on and so forth. So let's see how to come up with a basic block, because we said the basic blocks is what we represent as vertices in our CFG. So a basic block is a sequence of consecutive statements that have a single entry or a single exit, that you enter that block of statements from one point in the code and you exit that block of statements from one point of the code. So flow of control only enters at the beginning of the sequence, and flow of control only leaves at the end after the last statement. So there are many variants to computing basic blocks. We'll stick with the simplest just so we're able to understand the concept. But there are others that allow single entry, multiple exit, multiple entry, single exit, etc. But right now, we'll just focus on single entry, single exit. So how do we generate CFGs from intermediate code? So we're assuming first we have to identify a basic block. So partition the intermediate code into basic blocks, and you've seen what a basic block is, right? It's a sequence of statements that have a single entry and a single exit. So once you come up with your basic blocks, we then now add edges corresponding to the control flow between the blocks. Control flow through the statements either is an unconditional go to. From this statement, you must go here, maybe jump to a certain label, or it's the result of a conditional go to. If a certain test is true, go here, else go there. So you have multiple edges. If there is no go to at the end of the basic block, then of course, naturally, the control will go to the first statement of the next block because it's a sequential flow. So once then we add those, we come up with the edges that show us how we move from one basic block to the next. So let's do an example. So you said here the input coming first, the first step is to come up with the basic blocks. So the input to this partitioning is a sequence of intermediate code statements. How do you determine the basic block? You must identify a block, and the block starts with a leader and all the statements before the next leader, before the next block. So first determine the leaders, and these are the first statements of the basic blocks. What is the criteria for a statement being a leader? So the first statement in the sequence of the intermediate code statements is a leader. Any statement that is the target of a go-to, whether it's conditional or unconditional, is a leader, because once control is transferred to that statement, that is the beginning of a new code basic block. It's a new group of related statements. So a statement that is a target of a go-to is also a leader. And then any statement immediately following a go-to is also a leader. So in case it's a conditional go-to, if the condition is not met, control will just continue sequentially. So the first leader after a go-to is also then should also be a leader, because it's now demarcating a new group of related statements. So for each leader, its basic block is the leader and all the statements up to and but not including the next leader. Okay. So let's do an example that shows us how to identify basic blocks. So you said the input is a sequence of intermediate code instructions. So here we have 30 intermediate code instructions. And what we want to do first is to identify the basic blocks. So you see the basic block is made up of a leader and all the statements up to, but not including the next leader. We've been given the criteria for identifying the leaders. We said the first statement in the basic block, in the sequence of intermediate code instructions, is a leader. So in this case, of course, this is going to be a leader because it's the first statement. And then we said any code that is the target of a go-to is also a leader. So here we have a go to 5. So 5 is a leader. Go to 9. 9 should also be a leader. 23 should be a leader. And then the other criteria was any statement after a conditional or unconditional go-to is also a leader. So in this case, 9 comes after this go-to here. So 9 is a leader. 13 is also a leader because it follows 12. And 23 is also a leader because it comes after a go-to. So once you do that, we're able to identify our leaders. I hope that is clear how we have identified our leaders. And then from there, Now the basic block is the leader up to and not including the next leader. So the first basic block from this leader would be from statement 1 until statement 4. For this one will be from statement 5 until statement 8, and so on and so forth. So we partition, we identify our basic blocks like that. So here we have 1, 2, 3, 4, 5. We have 6 basic blocks. So I hope that is clear. Then now the next thing to come up with our control flow graph is to add edges depending on how the flow of control is passed from one basic block to the next. So for here, from this first basic block, where does control go to? Am I talking to myself? Where does control go to from the first basic block that starts from statement 1 to statement 4? When you're done with statement 4, where do you go next?
5.
We go to the next block that's between statement 5 and 8. Then for that second block, where does the control go to?
It's conditional.
9.
I've heard somebody saying 9. Only 9?
5 or 9.
Yeah, it will be 5 or 9. So it will either go back to 5, because if T3 is less than V, it will go back to 5. If it's not, it will go to 9, and so on and so forth. So once we're able to do that, we then are able to add our edges. Yeah. So now remember the diagram we started with here. We started with this. So these are the basic blocks. And then we're now adding edges from the first basic block somewhere. So this is what we're actually doing now, but we're using a different representation. So once you have the basic blocks, we then add the edges that shows how control goes. So from first basic block, we go to the second basic block. Second basic block, you could either go to the third one or you come back to the second one. From the third one, the same thing, you could either go to the fourth one or you come back to the third one. From this one, you either come here or you go here. From this one, you go like that. Okay, so I hope that's clear. So we've come up now, we've understood the basic blocks. Please give me a second. What is 1 minute? Okay. Yeah, so you've seen how to identify a basic block and how to come up with a CFG. So remember, we are doing this because we want to use now this information where we know what's coming in the future to help us in terms of the issues we've talked about: memory allocation, so register allocation, scheduling instructions. With that information, we're able to take better advantage of what's happening globally in the code to make global decisions as opposed to just translating each IC code into target code. That's why we're doing this. So now let's come and discuss instruction scheduling. We now have access to the global information. So we should be able to now use that information as we schedule our instructions. Okay. So this is stuff you've done. At least we are aware of what happens when we're scheduling instructions. So the challenge here is choosing the order in which instructions will be executed so that we utilize the CPU resources, the resources of the target architecture in the best way possible. So you were talking about the CPU. We don't want idle time. We want the CPU to always be running. We want to make use of the registers in appropriate ways, etc. So supposing we are using a RISC pipeline architecture, so we know that the sequence for executing instructions. First, we fetch the instruction, then there's the instruction decoding, there's executing, then there's memory access, and write back. Yeah. And we said that for RISC, there's an instruction being completed with every clock pulse. So pipelining, if you remember, I'm sure you did this, when the first instruction is fetched, when it's being decoded, the CPU can fetch the next one. When the first one is being executed, the second one is being decoded, we can fetch the third one. So at every given time, there is something happening. Yeah, so that's how the pipeline architecture works. So all nice and good, but we know that there are hazards that can occur, and we need a way to overcome these hazards. Okay. So the first hazard are what we call the structural hazards, and this is when machine resources limit the overlap. So for instance, if you have very few registers, it might limit what you can do. You'd have to first stop and free some registers. Or if there's some very unique structural limitations in the given architecture, or constraints rather, not limitations. The other one would be data hazards. And this really happens when, before another instruction can be executed, it must wait for a previous instruction to complete because it needs the result of the previous instruction as an operand. So that can actually also delay or interfere with the pipelining per clock pulse. The last one is also control hazards. Branching is especially notorious. Branch instructions are problematic because until they are fetched, decoded, and executed, the processor does not know which instruction will execute next. We may be jumping to a different, maybe go to statement 5, or we may be continuing to the next basic block. So that's usually a challenge. So many processors overcome this by speculatively fetching and decoding the immediately succeeding instruction in case a branch is not taken. So it assumes you're not going to take the branch. So it continues to work on the next instructions. If by the time it's done executing the branch conditional, if you find that actually it should have taken the branch, then the instruction pipeline is emptied and the branch target is fetched and execution continues. So it's almost saying, let's not just be idle. Let's continue as if we're not taking a branch. In case you're not taking a branch, nothing will have stalled. If we're taking a branch, then we're just going to have the risk of having to empty the pipeline and start again. Yeah, that's how most pipeline processors overcome the control hazard. Now, the other hazard is what we're calling the data hazard. And the data hazard is caused by memory latency. That reading and writing for memory is a bit slower, and it can cause the pipeline to stall. So the example shown there, we are loading what is the memory location stored in register R2, and want to load it into R1. And then we want to then use the result, what is in R1, into the add operation. So the second sequence, the add instruction, would stall until the memory access completes. So if memory access is not completing in one clock pulse, then it's going to stall because it has to first finish loading so that now we're able to continue. Yeah? So we can't add until register R1 is loaded. So that's an example of a data hazard. Then the other one, so that is memory latency. The other data hazard is occasioned by instruction latency. Now, under instruction latency, here, if we assume, for instance, like floating point can take 2 execute cycles, it means every time we have a floating point instruction, there will be 1 clock cycle where there will be a stall. So for instance, the first instruction, we are adding 2 floats stored in R2 and R1 and storing the result in R3. So we are saying if execute for float takes 2 cycles, you can see that in the second addition, we cannot start executing until the second cycle for the previous instruction completes, so that now we have the value of R3, and then now the execution can start for the second add. Yeah, so that's instruction latency. So these are things that we need a way to handle. So how do we deal with data hazards as we generate our code? Because remember, we want to ensure that the code we are generating is efficient. We want to reduce as much as possible, especially in this case, we're talking about a pipeline architecture. We want to take advantage that the fact that we can pipeline that at no given point is the CPU lying idle, right? So how do we overcome this? So the typical solution is to change the order of the instructions. Okay, so we reorder the statements, and we need to do this without changing the outcome. What the programmer intended must still be achieved. So what we talked about correctness. So we can change the order, but we can only change the order if we understand the relationships between the statements. And that's why now the CFG comes in handy, because we're able to see what is coming next, what data will be needed when, so we can take advantage of that information to reorder the statements and ensure that we avoid the stalls as much as possible. So we use that information and come up with different schedules. So many operations have non-zero latencies. So we've seen examples of memory latency, instruction execution latencies, and it's not possible to just have non-zero latencies. So the way we overcome this is to create schedules that minimize the latencies affecting the execute time. So in this case, execution time is order dependent. The way you sequence your instructions can result in either a shorter execution time or a longer execution time. So for example, if these are conservative latencies that have been assumed for different operations, so for instance, a load maybe takes 3 cycles, a store takes 3 cycles, a load and an add take 1, etc. A floating point add takes 1. Supposing now for each processor, we know the cycles it takes to perform a specific operation. So we want to make sure that we fill the issue slots where there's a longer wait. So for instance, if you're doing a memory load and you know you need 3 cycles, you can change the order of instructions to maybe to do the ones that are taking 1 cycle. You can do 3 adds as you're waiting for the load to complete. Yeah, and once we do that, of course, without changing the meaning, then we ensure that we are more efficient in terms of the time it takes to complete or to compute a certain sequence of instructions. So this is an example of how a different schedule can affect execute time. So we have an operation there, W times 2 times X times Y times Z. The result is stored in W. So here we have 2 schedules. So there's schedule 1, where you first load W and store it in T0. Then, because we're doing times 2, you just add. So you add what is in T0, and store the result in T0. So that we've done W times 2. And then you load X into T1. Then you do now W2 times X. We do the multiplication. Then you load Y. You do the multiplication. You load Z. You do the multiplication. Then you store the word. So that's going to take us 21. At time 21 is when we'll complete this schedule. The other schedule first does all the loads. So loads W, X, and Y. Then it does the W times 2, and it does the W2 times X. And then it loads the Z. So you can see here, as it's loading all this, it's able to do, when this one is completed, it's able to quickly do this. As it's loading this, it's able to continue multiplying what had already been loaded before the X and the Y. So this actually takes, it's done at time 14. So you can see the same result, but one is much, much faster than the other. So this is just to demonstrate to us that the order in which we sequence the instructions by taking advantage of trying to minimize the latencies can result in faster compute times, because we're using the resources more optimally, which is what we want our target, our code generator to be able to do. And this can only happen if we have a global view of the code and we're able to take advantage of reordering the instructions appropriately. So the other hazard we came across is the control hazard, and we said branching is pretty notorious. So here we will stall if a branch is made until the results of the branch is completed. Then we know what next instructions should be done. Yeah, and we said that for branch scheduling, branches take longer. They take more number of cycles to complete, and they create delay slots. So for instance, if you're comparing A, compare B, and then decide what should happen, so that can create a delay slot. So a compiler will try to fill these delay slots with valid instructions. So rather than do a no-op where nothing is happening, it can reschedule, it can move instructions around that are not dependent on the branch to continue executing as we wait for the branch to complete, and then the results of the branch will be available and we carry on. So I hope it's clear why we need the CFG, because you're only able to reorder these instructions if you have a global view of what's coming in the future, right? You know that I can be doing this, or in fact, the results of this branch do not affect this set of instructions, so I can be doing these ones, okay? So I hope you're beginning to appreciate actually the code generator part is pretty complicated, because now you are dealing with actual resources of a specific target architecture. It's unlike what we're doing with the intermediate, which is just from the AST, you just come up with as many temporaries as you need. Now here we have to be more sensitive in terms of um, the execution time, the ordering of the instructions, etc. Now the last issue that has to be addressed is register allocation, and this is also pretty complicated but very, very important. Yeah, so here the issues we are asking is, how do we best use the limited number of registers, and noting the constraints that we have special purpose registers, and also we have operators that require multiple registers. Now we recall that intermediate code uses as many temporary variables as necessary. Actually, practically any result can be stored in a temporary variable. So our intermediate code is going to necessarily have very many temporary variables. And in fact, in most cases, it might have more temporary variables than there are registers in a given target architecture. You may generate like 60 temporary variables for a piece of code, and perhaps your architecture only has 8 registers. Yeah. So we have to find a way to manage, as we're translating our intermediate code to target code. You see, we don't have the luxury of 60 registers. So we have to go to figure out which values do you write in memory, so that you have only the ones that you need in register, keeping track of what values are in which register, when to move them to memory, when to bring them back into the register, etc. So we need to be able to do this. And of course, at the back of our minds, we want to reduce the load and store operations, because we saw they're expensive in terms of the cycles needed to complete them. We also have to ask ourselves, what are the best values to keep in the registers? And we can only answer that if we can see ahead to know which values will still be needed in the future, so that you don't write them to memory. You retain them in the registers, so that you reduce the load and store operations. In the same breath, once we look ahead in our CFG and we're able to see, oh, we won't need this right now, we can write it to memory and free up some registers that can be used in the near future, based on the current basic block that we are rewriting. Yeah. So having many temporaries complicates the final translation of the code into assembly, but we know that it simplifies code generation as well as optimization. So it's a trade-off. The temporaries make it easier for us to move from the AST into intermediate code, but then it makes it harder to move from intermediate code into the target code. So it gives us the register allocation problem. So the register allocation problem, we can describe it as the need to be able to write the intermediate code to use fewer temporaries than there are machine registers. So we want to use fewer temporaries, that the temporaries we're using should not exceed the registers that are available for our target architecture. So we need a method that allows us to assign many temporaries to a single register, but without changing the program behavior. Yeah, we don't have the luxury of maybe 50, 40, 60 registers as we do, that we can create any number of temporaries. So how do we manipulate our intermediate code so that we're able to fit the many number of temporary variables into the available registers for the given architecture that we're targeting. So that is really the register allocation problem. Now let's look at the algorithms that are used to do register allocation. Now for register allocation, we are going to use the same information, the basic blocks, and that's why it's so important to understand what a basic block is and to identify a basic block. We are doing it as human beings, but you can imagine if you're writing the code generator, you have to identify the basic blocks algorithmically. You have to have code that looks through your intermediate code and identifies the basic blocks, identifies the leaders, computes the CFG, and then uses that CFG. So necessarily that is pretty impressive coding to be able to do that. But in our case, what we want to do is at least understand what it takes to do code generation. So for your project, I won't expect that you will do code generation. We'll stop at intermediate code generation, because now this bit becomes a bit more complicated. You'd have to be very specific about an architecture. And with the time we have, we're not able to go to that level. But at least if we can come up with intermediate code, the rest at least be able to understand what would happen. It's really just implementing these algorithms that we're talking about. Now, for register allocation, we definitely need two pieces of information. We need local information, which is at the level of the basic block. And then we need the CFG, which gives us the global view of the code. Okay. So there's that notion we're going to introduce called liveness information. And we'll look at liveness within a basic block, and then how to use that information to allocate registers, and also take advantage of global liveness based on the CFG to figure out what values will be needed later in future from the current basic block based on where control is going, and then now make a decision on what values to have on register, what values to move to memory, depending on the global liveness information. So I want us to now talk about at the local basic block level, how do we identify the liveness information? So for the basic code generation, we want to, remember we've segmented our intermediate code into basic blocks. So we're first going to come to each basic block and generate code for that basic block. And then using the global liveness information, figure out how to reorder either our instructions or the use of our registers in line with the CFG control. So we deal with each basic block individually. We compute what is known as the liveness information for that block. And then using this liveness information, we generate code that uses the registers in the best possible way for the statements that are in that basic block. At the end, we generate code that saves what we call live values, things that must remain live for the future. We say that either we save that in registers or we decide what to do with it. And of course, that will also be informed by the global liveness information from the CFG. So let's see how we compute liveness information for a basic block. So let's first define what we mean by liveness. Yeah. So liveness, and before we go to the formal definition, we're basically asking for a given basic block, which values must be live, where live means they're available in our registers. We don't have to fetch them from memory. They should remain in our registers for efficient and quick computation. Okay, so that's what liveness means. So the formal definition is as shown there on the slide. So for some statement S in the intermediate code, we say that variable X is live if three conditions are met. One, there's a statement within this basic block for which S is a statement that uses X. So we're saying there's a statement T that uses the value of X. There is a path in the control flow graph from S to T. Yeah, that from statement S, we're going to go to statement T. There's a path that will take us to T. And between the path between S and T, the value of x has not been changed. So there's no assignment to x on some path, meaning that the value that x has must be retained because it has to be used before it is assigned. So a variable is live at a given point in the source code if it could be used before it is defined. Yeah. If we're using it before we change its value, then it must be live. I hope that's clear. So in short, liveness tells us whether we care about the value held by a variable within this current basic block or not. And if it is live, we had better keep track of where it is and keep it in an accessible place, which is preferably a register, because we're going to use it before we reassign it and we care about its value. So let's look at some examples so we see how we determine liveness. Okay, so here is sample code. We have 6 statements from our intermediate code, so these ones. And we're asking, when is variable A live? So remember, we said A is live for a given statement if its value can be used before it is changed, and there is a path from a given statement to the statement that is using A. So here, the value of A is being assigned. So B and C, there's a value of B and C somewhere. Maybe it came from the previous basic block, but we have assigned the value of A. Now, T1, this statement, this statement here, A is live because we're using the value of A before we change it. So A has been set somewhere else, but we're using that value of A here. So A is live for this statement. The same thing, B is assigned T1 plus A. A is live because its value is being used as is, whatever it was set, we have not changed it. Here, we're not dealing with A. Here, we are reassigning the value of A. So A is not live for this block. Yeah, so I hope that's clear. So if you assume that A, B, and C are used after this block, then A will also be live here because we want to store its value because we know it's going to be used in the next basic block where control of flow of control will be sent after this particular statement. So when is B live? So B has to be live before this statement. So B was set somewhere else because here we're using the value of B before we set it. So for this statement, A is assigned B plus C. B has to be live, even C in this case, because we're using those values before we set them. Here, there is no B. Here, we are changing the value of B, so B is no longer live. We don't care about the value of B here because we are setting it. But here, we do care about the value of B because this statement C is using the value of B that preceded it. So we need the value of B here. Even for this statement, T2 is C plus B, so the value of B is live. And then here it's not. If it is used after this block, then it remains live. So I hope it's clear what we will say when we mean that B is live, what liveness means. It's asking for each statement in our code, what values do we care about, because we need to use those values as is because we're not modifying them. They've been modified elsewhere. So those values must be available for us to use to be able to perform this statement where that value is live. So let's look at an example of how we compute the live status in a basic block. So we've shown you, I hope you understand what liveness means. Now we're going to look at an algorithm that computes liveness for all our variables. So the input to this algorithm is a basic block. And remember, a basic block is a sequence statement starting with a leader up to where control flow passes to the next leader or to the next block. And the output is for each statement in the basic block, we must have the set of live variables. So for every statement in the basic block, we must show what variables are live for that statement. So algorithm says initially, all the non-temporary variables go into the live set. If we call our live set L, we'll have all the non-temporary variables going there. So for instance, in this code, sorry. Oh gosh, where did I go? Sorry about this. So for instance, in this example, the non-temporary variables are A, B, and C. T1 and T2 are temporary variables. So we're saying for our algorithm, all non-temporary variables must go into the live set. And then for I equals last statement to first statement, so we're going to start at the last statement in the basic block and work our way upwards or backwards. For each statement of the form, X is assigned Y ops. Remember, after we're dealing with quadruples, there's at most one operator and two operands. Okay. So for our statements which are going to have a result and an operator and two operands, we're going to attach set L to statement I. We are going to remove X from statement L, from the set L, and we're going to add Y and Z into the set L. Remember, L is the set of live variables for a given statement. So initially, the set L will have all the non-temporary variables. Then now we go modifying the values in this set for each statement. And we start from the last statement to the first. So if the statement, so of course here the value of X is being changed. So X cannot be live for this statement. That's why we're removing it. And then for us to compute X, we must have the value of Y and Z. So it means Y and Z must be live for us to do this statement. That's why we are adding them to the set of live variables. So let's look at an example. So here we have our 6 statements from our IC code, and what we want to do is compute the liveness, the live set for each of the statements in the basic block. So algorithm says at the beginning, put all the non-temporary variables into set L, which is what we've done here. Live is A, B, C because there are 3 non-temporary variables. Then now we work our way backwards. Yeah. So now we ask for this statement, what is going to be live? So we've said we're going to remove A from the live set and add the operands into the live set. So that tells us, so here A is live. So we need to remove A because A is being assigned, and we're going to add the 2 operands. So what is going to be live for this statement will be B, C, and T2. What do you expect to see here? What is going to be live here?
B and C.
Okay. We'll have B and C. This one.
T1 and B.
T1. Yeah, B and T1. This one. So we're now looking at B and T1, and we're looking at these guys here. So we're going to remove B. We'll be left with T1, then we add A. So we'll have A and T1. Then if we have A and T1, and we are working on this one, we're going to remove T1 because it's being assigned, and we just have A because A is already in the set. So we'll have A. And this last one, what is going to be live?
B and C.
Yeah, we'll have B and C. Okay, so that's what our algorithm is telling us. So that's how we compute the liveness, the live set for each statement in our basic code. So what does this mean? B and C are live before we come to this, because remember our basic code is starting. This is the leader of our basic code. So this means that B and C are being computed in the basic block that came before this, and it means they must be maintained in the registers. They must be live because they will be needed here. So you don't want the previous basic block to save this to memory. Yeah, if you're using global liveness information, if you can now see that actually you know that B and C need to be live for this basic block, then it makes you're able to make a decision what to do with B and C at the end of the previous basic block. Yeah, so it means that this is being computed in the previous basic block, and we need to store this, keep this preferably in registers because they will immediately be used to compute the value of A. You don't now first go and again load memory and then do the addition. So we've shown how we deal with each basic block individually. We compute the liveness information for the block. Now, what we want to do is to use this liveness information to remember the problem we're trying to solve is register allocation. So we've seen we're dealing with register allocation per block. But before we can do efficient register allocation, we have to identify the liveness information for each block. We've shown you now how to do that. So we have to compute the liveness set for each statement in a basic block. Now we want to use that information to generate code that uses the registers available to us in the most optimal way. And then at the end, we generate code that saves any live values that are left in register so that we don't lose those values. So I want us to now look at how we actually get to do that. So remember now our problem is that we have the liveness information. We want to use that now to generate code that allocates registers in an optimal way. From the leader of the basic block to the end. And for each instruction, we want to use registers whenever possible. I think it's obvious why we want to use registers, because if the values are in the registers, we reduce the load and stores, which are very because of memory latency. If they're already in the registers, then we just reuse and it's faster. So we want to, as much as possible, have most of our values in the registers whenever possible. If we come across a value which is no longer live, we can discard it so that we free that register. So that if we know that a value is no longer live for after a given statement, we can reuse the register that was holding the value of that variable. So the code generator has to track two things. It has to track the registers that are available for that target architecture, so that we're able to figure out which registers are available at any given point in time. Yeah, if you have maybe 3 registers, you have to know at any given, after each instruction, which registers are available. Then the other thing the code generator has to track is the location of the values. So the addresses, where do we find the values that we are dealing with? So here we have the non-temporaries as well as the temporaries. So we need to keep track of that. And for both of them, we use 2 descriptors or data structures. So one is the register descriptor. So the register descriptor is used to inform the code generator about the availability of registers. It's now the register descriptor keeps track of the values that are stored in each register. So it knows which are the registers, which ones are free, and the ones which are not free, which values is it holding. Whenever a new register is required during the code generation, so the descriptor is consulted to guide in which for register availability. So that's one of the data structures we must keep track of. That's a register descriptor. The other one is the address descriptor. So here, the values of the identifiers that are used in the program could be stored in different locations. Yeah, they could be stored in the CPU registers, they could be in heaps, they could be in stacks, they could be in memory, or a combination of all these locations. So the address descriptor is used to keep track of the memory locations where the values of identifiers are stored. Yeah, so it will be able to tell us for this particular variable, it is either in memory, it is in a register, it is in a what, so that is the address descriptor. So I hope you've understood the 2 data structures, because now that's what we base our code generation on in terms of allocating registers. So let's look at an example. So we have this as an example of an instruction type. So X is assigned the value of Y op Z. So we have the quadruple op X, Y, Z. So here, of course, we need 3 registers, or at least 3 locations. We have 3 variables. We have Y, we have Z, and we have X. So the challenge here is we need to choose the register that will store X, the register that will store our result. So in this case, we can say we're going to choose Rx to be the register where the result will be kept. How do we determine which value, which register to choose for the result? So if our operands, Y or Z, is in a register T by itself, and it is not live, then it means we can overwrite. We don't need the value of that operand which is in T. So we can choose T to be the register that we use for the result X. If it's not in a register alone, or it is not live, then it means we need to get a register that is free. So if there's a free register, T, then we simply use T to be the value to store X. So we choose Rx to be T. If in fact there is no free register, then it means we must free up a register. And freeing up a register means we have to move a value that is in the register that is not needed right away and write it to memory so that we free up that register. Then, so you've seen the algorithm for determining which register to assign to the result. Then we want to find the register we are going to use for operand Y. So if Y is not in a register, we are going to generate load into a free register, or we can also load it into the register we've chosen for the result. Okay. The same thing, if Z is not in the register, we can generate a load into a free register. And of course, now here we'd have to consult the register descriptor to find out which one is available. And we can also load it into X, into Rx, the register for X, if it's not the one we've assigned to Y. If we've assigned X to Y, then we have to look for another register that's different. And once we figure out which registers to use, we're now able to generate the target code instruction, operator, Rx for the result, Ry for operand Y, and Rz for operand Z. I hope that's clear, the logic to determine which register to use, because we have to have a register for X, a register for Y, and a register for Z. Then now once we do that, we'll update the information about the current best location of X in the address descriptor. If X is in a register, we're going to update that register's information in the register descriptor. We're not going to say register, maybe T0 is holding value X. If Y and Z, or either of them or both of them, are not live after this instruction, then we update the register and the address descriptors accordingly to show that those registers are actually available, that we can overwrite what is there because those values are not live, they're not needed in the after that statement. So there are two things. So first is figuring out which registers to use so to be able to generate the target code instruction with the correct use of registers, and then updating our data structure, so the register descriptor and the address descriptor, to reflect the choices we've made for the registers. So let's do an example. The same code we have with our 6 instructions, we have the liveness information. Yeah, so we know that after this statement, this must be live. Okay, after this statement, this must be live. So we use that information. So our algorithm, we now go step by step. So remember, we have the 2 data structures. We have the register descriptor and we have the address descriptor. So initially, we assume all our registers are available. For this example, we are going to assume we have only 3 registers at our disposal. So we have T0, register T0, register T1, and register T2. And we're saying they're all empty. So this is register T0, register T1, register T2. And because we have not said what contents they have, it means they're all empty at the beginning. Then we have our address descriptor. Remember, we have 3 non-temporaries and 2 temporaries. So we have A, B, C, T1 and T2. And these are the best locations. So M just means it's in memory. So at the beginning, we assume A, B, and C are in memory. Then T1 and T2, they've not yet been allocated, so they're blank. Then now we start processing. So instruction 1 from our code, is the code we are using, is A is assigned B plus C. And what is live after this is, the live set after this instruction is A. So we are saying we have instruction 1, A is assigned B plus C, and the live set is A. So this means after we compute this, A needs to be live because its value is going to be used after this without reassigning it. So our algorithm says we need to allocate the registers for the result for operand 1 and for operand 2. Yeah. So remember, instruction said if the registers are available, we just assign. So in this case, we've assigned register T0 to hold the result for variable A, and then the same register will load B into T0 and will load C into T1. So because we're doing this, now we're able to generate this target code instruction. So load word B into T0, load word C into register T1, and then we do the operation, which is add. So add T1, T0, and store the result in T0 because we said the result for A should be in T0. So we've generated the code. Now the next thing is to update the descriptors appropriately. So for the registers, remember before we had said they were all empty. Now we know that register T0 is holding the value for A. So the value of A is in register T0. The other two registers are still, we don't care about them. And why don't we care about them? Because the only variable that should be live is A after this. So we don't need to keep track of B or C since they're not live. So they may be in the registers, but we are saying those registers can be overwritten because B and C, we don't really care. So especially for T1, because that's that we have used. So we are saying T1 has some value, but it's not live, so it's technically available. Then we update the memory value, the address descriptor. Now A, before it was in memory, now A is actually in register T0. B and C are still in memory. These ones remain unallocated. So if you followed what we've done so far after instruction 1. Instruction 2 is T1 is assigned A times A, and what should be live after this is A, and T1 should be live. So we now need to generate our code. Now A is live and it's already in a certain register. So T1 is our temporary variable. A we know is in T0. So already register T0 has a value of A. So we need, because it has to be live, after this, we're going to store it in a certain register and we are assigning it the next available register, which is register T1. Then now we generate the code. We already know A is in register T0. So our instruction will just be multiply T0, T0, and store the value in T1 because we've decided we're going to store temporary T1 in register T1. So we generate that. Then now we update the descriptors accordingly. So right now, A has to be live and T1 has to be live. So A remains in T0. So we're saying register T0 has the value of A. Register T1 has the value of temporary T1. Register T2 is still unallocated. Then the address descriptor value A is in register T0. B and C, we still don't care about them, they're still in memory. But now temporary 1, we have stored it in register T1. Okay. So I hope you get to see, and I want you to visualize writing this code. That for everything you have to keep updating your descriptor so that the code generator at any given point knows which registers are available and what to do with them. Instruction 3 says B is assigned T1 plus A. What needs to be live is B and T1. So now here we note that A no longer needs to be live. So that's important to note. So since A is not live after the call, so we can use T0 to store the value of B. Yeah, because we now do not need that value of T0. And then T1 is already live and you know it is in register T1. So we're going to generate the code, add T0, T1, and store the value in T0. So now we know that the value of B is what is stored in register T0. We update the register descriptor, so B goes to T0, temporary 1 is still in register T1, and we update the memory location. So here what has changed is B is now in T0. And we continue doing the same. So for instruction 4, we have this, we have the liveness, so B and C must be live. So what we note is that T1 is no longer live, so the register that was holding T1, which is register T1, can be reused. So B is already live, so it's in a register. So we're going to read temporary 1 from register T1 and use register T1 to store the value of C. So we generate that target code instruction. So multiply T0, register T0, T1, and so the results in T1. Update the descriptors as appropriate. So B is in T0, C is now in T1, and the best locations now for B and C are in the registers. And we continue doing this, okay? So we have instruction 5, the same thing. In this case, now we have a new temporary variable that is T2. B and C are live. We already know their locations is T0 and T1, and they have to be live as well as T2 also has to be live. So now in this case, we must use register T2 because B and C have to be live, so we cannot overwrite register T0 and register T1. So the register to hold the value of T2 is going to be the third register T2. So here we are going to generate add B and C and store the result in T2. And then now we update the register descriptor to show that now temporary T2 is the one that is stored in register T2. And here we're also saying T2, temporary T2 is in register T2. Temporary 1 is no longer, we don't care about temporary 1 at this point. B and C are in the registers, A is in memory. Then instruction C, this is the last one. So we had A is assigned T2 plus T2, and what should be live is all the non-temporary variables. Yeah, and note that now this is going to influence the next basic block. So these values are needed. They're needed. So here, T2 was in register T2, so we basically just add, and we've stored the value in T2 because T2 is no longer live, but B and C should be live, so we can only use T2 to store the value of A. So T0, we update the descriptor. T0 has value of B as before, T1 has a value of C, and now A is stored in register T2. And we update now the best locations. So we know that register T2 has a value of A, register T0 has the value of B, and register T1 has the value of C. Now, as much as we know what values are in the register, we need to save these values so that they'll always be in memory. If you notice somewhere here, we said the best value of A was still in memory. What was that? This one. Yeah, it's because we hadn't overwritten it. So we know we didn't do a store word. So the value of A still remains. So that's why we need to do something like this. So at the end of that block, we want to store these values into memory in the locations for A, B, and C. All registers are available, but the values are still in the registers. All live variables have been moved to memory so that now once we enter the next block, depending on what should be live for that block, if they're supposed to be in the registers, then, because remember we said we assume they will be live at the next block. So they'll be in the registers, but also we'll have a copy of them in memory in case they're not live. Okay, in case now the next block has to overwrite those registers, we don't lose the values. That's why we have to do this. So we generate that. So at the end of that whole using the register allocation method, we're able to generate this as the target code for that intermediate code. The load word for B and C, then we do the add, the mult, blah, 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 and then we stop. And this is the comparison. So here the question is, how does this compare to the naive approach? Because remember we said the naive approach will generate for us very many instructions if you just go statement by statement. So of course, you can imagine for this assignment would have had almost 5 or so instructions, because for each were reading memory and storing to memory, read memory, store to memory. So we've significantly reduced the number of load stores. We have used even our registers, because our constraint was 3 registers. We've generated code that just uses the 3 registers. So even if we had maybe many temporary variables, we'd still only use the 3 registers. So this approach is definitely much better than the naive approach. And this is the approach that is used for register allocation. So liveness information allows us to keep values in registers if they will be used later. And that is really good for efficiency because it eliminates unnecessary loads. So of course the question is, why do we assume all variables are live at the end of blocks? Because if we assume they're live, then we have to write them into memory as well as they remain. So we're still generating the store words. So can we do better? Yeah. So the other question is, why do we need to save live variables at the end? Yeah, we might have to reload them in the next block. Of course, if there are some are in registers, that's okay, but some may actually not be in the registers, and we've decided to save all of them. So these are still questions, and there's a lot of algorithm enhancements to make sure that we reduce unnecessary, like use the global CFG to make this kind of decisions. Yeah, so what we've also described is a straightforward algorithm, but they're better enhanced. So we're going to stop here because of time. And this is a topic I don't think we'll finish in the remaining 15 or so minutes. So this is another approach to register allocation. So we've given you an algorithm that we can use, but there's another approach which is called graph coloring. And it also uses liveness information. And it uses the notion of, this is a problem in computer science, which is called graph coloring. That if you have this number of colors and a graph with this number of nodes, you find a way to make sure no 2 nodes of the same color are adjacent to each other. It's a bit complicated, but it's another very efficient way to allocate registers. So we're going to look at that in the next topic. Yeah, so we're going to stop there for today. Yeah, so we'll continue with that as a separate approach to register allocation. But the gist of today's lecture was really understanding target code generation as the last step in compilation. We'll just go back here to slide number 2. Yeah, so we're here. We're now generating the target language. And we said now everything we're doing here is architecture dependent. We now have to be, here we're not really concerned so much about efficiency and everything, especially when we're doing the intermediate code. But now here we're talking about efficiency, we're talking about correctness, we're talking about ensuring short execute times for the code that is being generated. So we have to be aware of the target architecture, what are the features that it has, if it's a RISC pipeline, if it's a CISC, if it's a vector processor, how are we using that information to generate the code? How are we scheduling our instructions so that we avoid latency as much as possible, and where we can't, we plug in other instructions so that the processor is not idle, especially when we're talking about pipeline architectures. Then the last and very crucial thing is allocating registers to adhere to the constraints of the specific architecture. So the need to understand what variables are live, and even before we can understand what variables are live, we've introduced the notion of basic blocks, control flow graphs, and then using that information to allocate registers and keep track of which register is holding what information. And for any variable, where is its best location? Is it in memory? Is it in a register? Where is it? Yeah, that's what we're trying to do today. So we are almost done. Actually, we are remaining just one last topic, which is on code optimization. But before we do code optimization, we're going to at least finish the graph coloring topic as another alternative to register allocation. And then we'll be done. So in terms of your project, by now you should be done with your puzzles, which you should be evaluating, I think, tomorrow. Your next task will just be simply to come up with intermediate code, right? So from your tree, which you now have, you're going to just use the naive approach. So generate code for every you look at the kind of nodes that you have and generate intermediate code instructions for each node in your tree. So now that's what you should start already working on, because I'll just give you another like 1.5 weeks to do that, because we need to complete that before the end of the semester. And then after that, we're going to do a cut. And remember, I said the bulk of this course is from your project. Yeah, that's why we just focus a lot on the work that you've been doing. But you still have to do a cut, at least one cut, and an exercise that I'm going to announce pretty soon on some of the topics we've covered. So we'll stop there for today. And we'll meet you tomorrow. Thank you, Aduma, for the thumbs up. Everybody else, let's have a good afternoon.